Hey everyone, today we're going to dive into something that's secretly running your digital life: sorting algorithms. Seriously, these are the powerful instructions that organize everything from your social media feed to your files. Understanding them is kind of like learning the secret language of computers. So let's get into it. But first, let's try a little thought experiment. Picture this. I hand you a deck of 1,000 playing cards, all shuffled up. What's your strategy to get them in order, fast? I mean, would you go card by card, compare pairs, maybe split the whole deck into smaller piles? This exact puzzle is what sorting algorithms are designed to solve. And as you're about to see, the strategy you pick makes a huge difference. All right, let's start with the most basic methods, the ones you might come up with yourself if you were actually sorting those cards. They're super easy to understand, but that simplicity, well, it comes with a hidden cost. First up is bubble sort. This one is a classic, and for good reason. It's incredibly simple. The whole idea is just to look at two items right next to each other. If they're in the wrong order, you swap them. Then you just slide over one spot and do it again, and again, and again, all the way to the end. Okay, so check this out. You can see it in action here. In the first step, the 9 is bigger than the 5, so bam, they switch places. Next, that same 9 gets compared to the 8, and they swap again. See what's happening? The biggest values are literally bubbling up to the end of the list with each complete pass. So here's the catch. While it's super easy to get the hang of, bubble sort is, well, kind of slow. For a handful of items, it's totally fine. But for thousands or millions? Oh man, the number of comparisons it has to make just explodes. It's a great way to learn the basics, but you would not want this sorting your company's entire database. Now, there are a couple of other simple strategies, like selection sort and insertion sort. With selection sort, you scan the entire list, find the absolute smallest thing, and just stick it right at the beginning. Then you do it again for the second spot, and so on. Insertion sort is more like how you'd actually sort playing cards in your hand. You pick up one card at a time and slide it into its correct spot among the ones you're already holding. So these simple approaches are a good start, but to handle huge amounts of data, we need a much smarter strategy. And that brings us to a truly revolutionary idea: divide and conquer. And this is the big question, right? Instead of trying to wrestle with that entire giant list all at once, what if we just broke it down? If we split that huge deck of cards into smaller piles, sorted each of those little piles, and then cleverly put them all back together, would that actually be faster? The answer is a huge, definite yes. This leads us to quicksort, and its genius is all about one thing: the pivot. All you do is pick one element from the list, it could be any of them, and you call it your pivot. Then you just rearrange everything else so that all the smaller items are on its left and all the bigger items are on its right. And just like that, the pivot is already in its final, perfectly sorted position. So what happens next? You've got two smaller, unsorted lists, right? One on each side of your pivot. Well, the really cool part is you just run quicksort again on each of those smaller lists. You pick a new pivot, you split the data, and you repeat this process over and over. This is called recursion. You keep breaking the problem down until you're just left with little lists of one item. And at that point, the entire thing is sorted. Another really powerful divide and conquer algorithm is merge sort. Now, its approach is a little different. Instead of using a pivot, it just methodically splits the list exactly in half, again and again, until it's broken all the way down into individual items. I mean, think about it. A list with only one thing in it is already sorted by default, right? And now, for the second half of the magic, the merge. Once everything is broken down into single items, the algorithm starts putting them back together. But it does it in sorted order. It takes two small, sorted lists and combines them into a new, slightly bigger, sorted list. It just keeps repeating this process until there's only one big list left, which is now perfectly sorted from beginning to end. Okay, so we've got these two families of algorithms, the simple ones and the divide and conquer ones. But how can we actually prove that one is faster? For that, we need to talk about the math of speed, which is a concept called Big O notation. So Big O isn't about timing an algorithm with a stopwatch. It's about understanding how its performance scales. It answers the most important question: if I double the amount of data I need to sort, does the time it takes also double, or does it quadruple, or something else entirely? It describes what happens as the number of items, which we call n, gets really, really big. Our sorting algorithms basically fall into two main speed categories. The simple sorts, like bubble sort, are in what we call O of n squared, or quadratic time. The divide and conquer ones, like quicksort, are an O of n log n, or log linear time. But let's make it easy. Let's just call them the slow lane and the fast lane. And this graph, this says it all. The line on the bottom is the number of items to sort, and the line going up is how much time it takes. Look at the O of n log n line for the fast algorithms. It curves up nice and gently. But the O of n square line for the slow ones, whoa, it shoots almost straight up. When you're dealing with tons of data, this isn't a small difference. It's the difference between waiting a few seconds versus waiting a few days. So this all leads to the ultimate question, the one you might even get on an exam. Which algorithm is really the best? And the answer, as it so often is in computer science, is, well, it depends on the situation. Check out this table. On average, quicksort is amazingly fast, but look at its worst-case scenario. It's O of n squared, the same as bubble sort. So how does that happen? It happens if you get really unlucky and keep picking the worst possible pivots, like the smallest or largest item every single time. When that happens, the divide part of divide and conquer kind of fails. On the other hand, merge sort is a guaranteed O of n log n every single time, which makes it way more reliable, even if it uses a little more memory. So here's the bottom line. If you're dealing with a really small list or a list that's already almost sorted, a simple algorithm like insertion sort can actually be faster because it doesn't have a lot of complex setup to do. But for pretty much every other real-world problem with big, random, messy data, the smart divide and conquer strategies like quicksort or merge sort are just exponentially better. And that leaves us with one last thing to think about. Every single time you see a list fall into place on your screen, your contacts, your emails, the files in a folder, one of these fundamental ideas is doing all the hard work. So next time you see that happen, ask yourself, was that the simple brute force of a bubble sort or the clever recursive magic of a divide and conquer?